Hi, my name is Thomas Brandt. We're doing our homework 5, I think.
That is
video.
correct.
All right, I'll be doing number 1 and 2. So we're given this this is a really bad drawing, but try to remember belt system. These are not quite gears, but you get it.
They
There's two of
transfer
these.
torque from one to another. One
Yeah.
axle to another.
So we have these 2 circular things that the belt is around there, and then they also have these rods sticking out of each one. And then we're given all of these values. With these values, it's always important to convert to the proper units. So with P for power, we're now introducing horsepower. Fun fact, a horse doesn't have 1 horsepower. But the average
Horse over the course of a day.
has 1 horse. Anyway, so we're going to multiply that by...
test?
I hope not. It should be 3.7, but we're going to multiply that by 6,600, which is what you want to multiply it to get it in pound inches a second. We're going to be using inches
So
here
that's
because
550
everything is
times
standard.
12. Because I remember we were talking
Yeah,
about 550.
or 550 in class. We'll leave that in PSI. And then we're also given these distances of the rods, the AB and DC. And then in our equations, we're going to have a C value, which is where we're going to use these, except you have to remember that these are diameter, not radius. C is for radius. So we're going to divide these by 2. And then this is the main equation you want to use. We use it in a couple of homework problems on this one. It's frequency is equal to power over 2 pi torque, or T.
Oh, so that's the same as the power equals torque. I think this is the one I was using right here. Power equals torque times...
Did you use that for this one, or?
Just
for
it's the same equation, just where...
Yeah, so we rearranged that. This was confusing at first, but we can also establish this identity of TB over RB is equal to TC over RC. That's going to be proportional, and that proportion is important. It'll allow us to figure out that a quarter of the TC is equal to TB.
So that's just the transfer of torque equation, right?
Yeah. So we can derive that.
I really love that.
For our T equation, we have our given. J is the polar moment of inertia, which for this kind of shaft, it's a solid shaft, so it's going to be pi over 2c to the 4th. And then, we just plug everything in. We'll get this Hertz value. For number 2, it's the same exact question, except they flip the radiuses. So, and literally all we need to do to solve that is you just replace them in the equation. Our ratio is going to stay the same. And that's it.
What's that sentence at the bottom?
The radii are swapped, so plug in new radii into the same equation and you're done.
Okay. Thank you. Sorry, I was just,
Yeah.
Just want to make sure that wasn't anything we were missing.
I think Case had a question on number 1.
I was really confused on this one. Because originally, why do you not switch these for the second part?
Yeah, so good question. So this is just the ratio difference between the big and small. I'm calling them gears, I guess. And because
It's
of
the
that,
same application for gears, correct?
Yeah, exactly. It should stay the same.
Because I thought when you switch those, you would also have to switch.
That's
the
what I had done
ratio,
at first
right?
too, and that will not get you the right answer. So I hope intuitively that kind of makes sense, and how we rearrange this equation.
Because even though those switch, B and C stay the same.
Yeah.
The radius. Okay. That does make sense then.
All right. Moving on to number 3 here. We're given I don't even know what you'd call this, but it's got it's a nice little fillet. And so we're ultimately trying to find step shaft. Yeah, I like that with a fillet. So the fillet's going to help reduce the total amount of stress concentration on this. Instead of a right angle, as we talked about, it's going to be a gradual. And so we're going to go ahead and try and find the frequency, the minimum frequency that we can run at here. So the first thing we're going to go ahead and do is find out our K value, which is the constant for, what's that called? Is it just the constant for the fillet? The concentration constant or something like that?
Stress concentration factor?
That might be it, yeah. So using our fillet radius, which is 6 millimeters over the diameter of the smaller portion, and then our big D over little d, we can go ahead and get these two values, and then you just take these two values and you're going to plug them into the graph, which will be provided on the test, or like I think it's in her slides, whatever, and you're going to get a value of 1.25 for the factor.
There'll always be, yeah. So the D in the numerator will always be the bigger diameter, right?
Yeah. So the big D is always going to be over the little d. So big D is the diameter of the larger part of the.
And that's a different
shaft.
radius than the diameter that we're using in that one. Yeah.
Say again.
Yeah.
What about it?
That radius is different than the diameter we're using in the denominator.
So this,
that's the fillet.
That's the fillet.
That's the fillet
Yeah.
radius.
Yeah. So this is fillet over little diameter, and then this is big diameter over little diameter. And then with these two values, you'll go ahead and use this value to find out which curve you're using, and then this will be your x-axis plot, and then you should get a value of 1.25 for your factor.
Nice.
And then, so we're going to go ahead and plug k into the equation. And so this is the same equation that we've been using for before, Tc over J. But now we have a k in it. So that's just when you have a stress concentration, like a hole or a fillet, that's what you're going to be using. So it's pretty much the same thing. And then we'll go and plug in our tau max, and then we have our k value, and then plugging in for the diameter. It's important to note that you're always going to use the smaller diameter when dealing with the stress concentration, because obviously that's going to be your that's always going to be your weak point, your point of failure. It's going to fail first. So we're going to go ahead and use that smaller diameter, or smaller radius, excuse me. C is radius.
That's right.
So then you can go ahead and get a force of 169 pounds, and we can go and plug this into the power equation, and then we'll convert this omega into a frequency value, which is what we're looking for.
So we could have used that equation up there.
Yeah, so the way you did it is you just directly kind of interpreted it as isolating for a frequency, where I solved for the omega and then transformed it, but yeah, so same thing. But yeah, there you go.
So the fillet radius is only, like, the only reason we want the fillet radius is for that k, the constant?
Pretty much, yeah.
Okay.
Yeah.
'Cause, like, just like instinctually, I was trying to use it for, like, solving torsion, but obviously that didn't work.
Yeah. Okay.
We can flip it?
Yeah, I think so.
We should have had, like, a shirtless dude behind it. When it flips, it reveals.
It's still recording.
Okay, my name's Case. I'll be doing number 4. So we're given a cantilever kind of diagram here with a loading force from A to B with length A and the entire level with length L. And it's saying what are the diagrams and the equations we can use here. So, what's this called again? Shear stress. So yeah,
the shearing and moment.
For the shearing diagram. So we start at 0, and if we start at the free end of the diagram and we move across it, we're going to start at 0, whatever, pounds, or I don't know, units of force. And as we move along this axis from A to B, along this length A, we're going to slowly get more and more force loaded upon it. So, and since it's downwards, it's negative force. So when we start A at 0, we're going to go lower and lower as we keep increasing that force and that pressure. And for moment, the bending moment diagram, it's just the integral of this. Or no, derivative. Wait.
I think it's
integral.
You have integral written on there.
Integral, yeah. So
depends which way you're going.
Well, it's because, like, if this is a negative line, this is negative x. This would be like negative 1/2 x squared. So it's a negative parabola.
So that's what I'm saying. I was gonna say what helped me realize is, like, so here, number one, we have if this is your x-axis, this is negative value and negative value. So both of these are going to have negative slopes. Mm-hmm. But then, like you said, here, this is negative x. So it's changing with respect to x squared. So it's parabola. And then once you get to a constant line, you can see a linear relationship.
Yeah, thank
Anyways,
you.
yeah.
That makes sense. And then, so for the equations, just like we said, we know that the shear equation is negative omega x, and just taking the integral of that, you'll just get the integral negative omega x squared over 2. And then the other possible equation, so that's for the entire, anywhere along that. And another possible equation that you could use is just between A and B using this A length. If you choose a point within that and you want to take the moment about that, instead of taking an integral, moment is just force times distance, and since we know the force is already omega A, that's our force, and our distance from the center of the, because if we treat AB as just one direct force thing in the middle, the distance from that will be your x position minus half of that. That's where you'll find yourself.
The center of the distributed load.
Yeah. So that's their distance from the center of the load. So that's the moment equation for that.
You done?
Yeah.
Okay.
Thank you.
All right. So we're doing 6 and 7. We're given like a series of bars, I would call it, I guess, and we have some forces acting on it. I already solved out the reaction forces. I don't think I need to go over it because it's just static stuff.
Yeah.
You do moments and some of the forces in F and X directions. So what we're trying to do is find the maximum shear forces and the maximum bending moments acting on this. And we're gonna find a graph of it and then just whatever the maximum is. I actually think it's easier to find the maximum first, because in order to do that, you go through each individual shear. I'll just go over the process. Basically, you start from the furthest point away, and you'll have one force there, and you will calculate the shear at that point. So here, there's a 2 kilonewton force downwards. The shear would just be the exact opposite of that. So you'd have a 2 kilonewton shear. And you keep doing that, you keep adding forces on and make a new cut every time in a new FBD. And eventually you'll find, to save space, I only went up until I found the maximum force. We only needed to do 2 of them for this problem, and you'll find that it's 12 kilonewtons. And then for the bending moment, it's pretty much the exact same thing, but instead of just the sum of forces in the y direction, you're doing it with moments. Did a few of them, but in the end you'll find that 2.7 kilonewton meters, I think, would be the
So
right
what are these
number.
points based off? 1, 2, and 3? Is that just like these points along this axes?
You mean like along these?
Like, how do you decide where you cut? Or...
So I cut. So I'd start here. We have one force here, so I'll cut. After
So you're just
that
checking
force.
the moment at every place which the force applied change.
And then you'll add one new force for every time you make.
Okay, gotcha.
And with that, like, do we just like when I was trying to do this problem, like I got to a point where, like the last if you go left to right, the last force, that last downward force is never considered in any equation.
Yeah.
There
So
is
that's-
no way to do that.
Because like what I was saying, like you'll have a force and you'll have some distance x after that force. When you get to here, like there's nothing after it. So what are you gonna do about it?
Oh, yeah. I had another question. I just forgot it.
Wait, so I'm just looking at your first one here. Is that this too?
Yeah. So like I started from this end because it's the furthest point.
Yeah.
So you have your 2 Newton force
Where's that
And
being?
then-
Is that being applied right here?
on the very end.
Oh, okay.
And
So
so-
if you're starting here, wouldn't that just be in line with the?
Okay, yeah, I guess it's kind of hard to explain. I've got this force here, and then I walk up to where the next force is being applied.
Oh, okay, like
so
right
it's
before
onto
it.
this line.
Okay.
So I didn't label it, sorry. Every like spacing is 0.3
Okay,
apart.
got you.
So I have 2, and then I'm gonna walk 0.3 meters to the
Okay,
next
but it's
one.
like right before that occurs.
Yeah,
Okay.
but you can just say like,
Yeah.
and then the next one. So this is still considered. So it's 2, and then it's gonna go all the way to the next force, which is 0.6 meters this time. but now we have this force down here, which we're going to include. So it's 2 times 0.6, like I just said, but then cx, which is 10.5 times 2, or 0.2, because this distance is 0.2. And then after that, we'll have the distance on this will always stay the same because it's just one length. I'm not actually moving up. This will become 2 times 0.9 because it's going to go from here all the way to this force.
I see.
So you're just adding a distance and a new force every time.
And like, it's okay if you don't know, because to be honest, I intuitively did it the same way you did. But like, let's say this force was like 12.
Okay.
It would matter, right, if we took the moment starting right to left rather than left to right. Wouldn't that change things? So because like if we're not considering the last point, do you know why, or like it's fine if you don't, because I intuitively also went left to right, but
Well, wouldn't that you probably get a whole different thing to be considering?
I'm almost wondering if we are supposed to take like an imaginary distance away and then.
What distance would you put? I assumed it. I basically had it like going back. I would do like 2
I guess that
times
doesn't make
0.
sense. Oh, okay.
But maybe,
I just wonder, like,
maybe like on these types of problems, I don't know. Maybe like it's supposed to be symmetrical to avoid that issue.
Do any of you, Case or Andrew, understand that?
Which part?
If like we both, I think we all arbitrarily pick to go left to right, and then as you're going through these equations, this last force is never considered.
I think ultimately, if you go right to left, you should end up with the same conclusion.
Even if this is like 12 and this is 2, and then I go this way, would that not be a different number?
It would be a different number, yes. Oh, huh.
Which could, in this case, it
I
wouldn't,
see,
but
I
it
see
could
what you're,
change our
I see,
maximum.
I see what you're saying. I think the reason is because we're considering this as a function of x right here. So you see how it's a function of x?
Yeah.
So we're going from x, like just naturally, x increases. So if, just looking at the axes, if we're considering this as our origin point, you're going to start there. And that's why. Right?
It's not fixed. See, with my example, it's fixed. That's how we start the free end. But these have 2 free ends.
Yeah, that's what I was.
So that's what I'm
wondering,
saying. I think it's just depending on how you're drawing your graph, you're putting the origin at that point. So I guess you could put it at that point,
You
but
could
then
do
your
it
graph
either
would
way.
just be different. Yeah, I don't know. I'm
Because the
not
whole
100% sure.
A bending moment is just a moment. You could take a moment anywhere you want. It's just for the maximum moment. The whole reason we take the max is that, excuse me,
Sorry.
like we're taking a maximum moment. So you want to start here. You could start here. It's like you're guessing and checking, but like you start here and realize that at here the most amount of forces are concentrated at this side.
So if this was like 120 or 1,200, let's say we started left to right and we're coming this way. It would be good practice. We should then go the other way for this and consider this whole length.
I think, yeah, you could do that,
Sorry.
and you can see that using a graph, you can see where like the most, because if this was 1200, you could say that this would be like all the way down here, and there's the most area, or like there's like the most area at that point. Because like the whole reason we took the bending moment from here to here is because the area under this curve is the bending moment. So like their most amount of area from one side to another is here, because instead we could have gone from here to here, but it's just greater to go from here to here versus from here to here or something. But yeah, if this was 1200, you'd see it like skyrocket, so you'd want to go from that side.
I suppose that makes sense.
I think that the key to like where you should start is like this diagram. That's why we did the diagram first. But that's how I understood it.
Well, we wouldn't be able to create our own diagram necessarily without the calculations. Like it just happened that this question gave it to us before.
No, in other questions you do make the diagram. This one gave us 4 diagrams and we chose the right diagram. So you could have figured it out, but intuitively we just knew that this should have been negative. That's why we chose this graph. But like in other scenarios, they'd want you to like formulate a graph using like equations.
Yeah, so you would work it out like.
Yeah.
These should be negative, by the way. because for sign convention on a shear, for just basic sign convention, this is positive, and this is negative shear.
Wait,
So-
that counterclockwise is positive.
No, I was looking at the lecture site. I could
Oh,
try
really?
to pull it up.
Is it opposite? Oh, maybe I'm
It's-
wrong. I just.
Well, yeah, because I was confused because I was like, why would up be negative? But yeah, that's just think shear is weird.
Huh.
All right.
Which you can also see by the graph. These are negatives.
All right. That was a good little discussion we had there.
It's still
Thank you.
recording.
Yeah, no, I know.
Thank you.
Oh.
All right. Any other?
I
We
think
good?
we're good. Bye. Bye, Brian.